Let's go ahead and start with analyzing cost behavior. When we're talking about analyzing cost behavior, we're talking about how do we actually use the numbers that we've looked at before and use them for projections. There are 4 different methods that we like to use. The first one is called the account analysis. The second one is called scatter plots. The third one is called the HighLow Method. And then the fourth one is called regression analysis. The first one is called the account analysis. And when we're talking about the account analysis, it's pretty straightforward. It's using judgment to classify each general ledger account, each expense account, and trying to figure out, well, how does it behave? Is it variable, or is it fixed, or is it mixed, right? So we're going to use our best judgment. We're going to break those expense accounts into those 3 categories. And then based upon that, we're going to use that to project the future and project future costs. So it's pretty straightforward, pretty easy. And frankly, that's what most companies use because it's the easiest. I mean, if you don't have to memorize any formulas, you don't have to do anything like that. You just simply go forward with your account analysis. The next element of the 4 was called the scatter plots. Okay, the scatter plot. And so the scatter plot is you're using graphs, historical cost data on the y-axis and the volume data on the x-axis. And we're just going to go back and just try to plot everything over a period of time. All right. And what this does, it helps the individual, the person that's analyzing. It helps the individual to visualize the relationship between cost and volume. Okay, so now you can see whether there appears to be any kind of a trend. We're just going to plot all of these volumes, all of these costs based on certain volumes, and kind of see if there's any kind of a sense of it. So if we see a linear pattern, then we can see a strong correlation between volume and cost. If we actually start to see a linear pattern as the volumes go up, we could see, even though there's kind of scattered around in different areas, if we can kind of make out whether or not there seems to be some kind of a pattern here, right? And so if we don't see that, though, we could have essentially just a random pattern, and then from there we're going to figure out that there's little or no correlation between the volumes and the costs. You won't see a line or some type of line be determined because there'll be no correlation. There'll just be numbers all over the place. And then what you also want to remember, that the term outlier, you learned this again in your statistics class, the outlier, and that's when we have some abnormal data points that we simply just want to kind of take those out of the equation when we're talking about statistical analysis. What we're really saying is that, that's really not that relevant. They're outliers. They just fall outside of the normal pattern. So generally speaking, we kind of want to ignore those. Okay, so if we get like a scatter plot graph up, we can actually see that there appears to be some correlation. And what you're going to do is just simply go through the process of plotting everything out on a graph and seeing where things fall. So, you'll look at the volumes. You'll look at, let's say, at volume of 19,000. You plot it. Boom. That's the cost was $40,000. You plot it. Then at maybe about 16,000, it was more like 140, 147 or something. You just go down and just start plotting it down. Maybe at about 25,000 units, the cost was about 202, 203,000. But what you'll do is, after plotting it out over all the different volumes, even though there's really no specific linear relationship, you can kind of see that there is a correlation, and you kind of see the pattern here, right? You kind of see like there's a line being drawn. It's not perfect in nature, like a true variable cost or even true mixed costs with the variable cost, but you do see that there's a bit of a linear pattern there. So So after looking at the scatter plots, we can then look at what's referred to as the high-low method. Okay, so like on this high-low method, essentially we're going to look at, it fits a mixed cost line through the highest and the lowest volume data points. So as an example here, we look at the high-low method, and in this case here, if we can see this closely, we'll see that maybe at the lowest point here, that actually the low point is 13,000. The volumes are 13,250. So we plotted this out. We noticed that this was the lowest volume that we had. And then, this is a bit of a scatter plot in place where they were at different places. But then we look at the highest volume area, and it was at 25,200 units. So when we plotted this out, we looked at production over the past history and started plotting this out. And we figured out our lowest point of volume was at 13,250, and then our high volume was at 25,200. Okay, so the high-low method, step number 1, find the slope of the mixed cost line. The slope is the variable cost per unit of activity. And to find that slope, we're going to take the slope equals variable cost per unit of activity equals rise over run, which in essence is the change in costs divided by the change in volumes. All right? And then you know that the change in costs are going to be the y, and the change in volumes is going to be the x. That's the x-axis and the y-axis. So as an example, they flip these up on us, but the units, which we know the units are going to be the denominator. The units are going to be the denominator. But we're looking like our January low was, or our low for our whole year was in January, and that was for 13,250 units. Okay? Our high for the whole year was 25,200, so we've got it plotted now, 13,250, and these are the units, so that's the volume, that's the x-axis, all right? The y-axis is the costs. The costs are low. The low was in January also, it was 114,000, and the high was 209,600. So even though these are flipped, we're going to essentially say that the change, the y-axis goes on top. So the y-axis is the costs. So it's going to be 209, that was the high, minus the low. 209,600 minus 114. High minus the low. That's what the high minus the low is. That's going to be the numerator divided by, that's the divided by sign, by the volumes, the x-axis. Well, the units are the volumes, right? So 25,200 minus 13,250, that is going to be our denominator, all right? And so we take the change in costs, and we're going to divide that by the change in units. And if we ran those numbers, you'll end up with $8 per guess. Okay, $8 per guess. And what does that tell us? Okay, so we'll go on to step number 2. After we have the dollar per guess, now then we can go into step number 2. And what we want to do is we want to find the vertical intercept, the place where the line intersects the y-axis, which really we'll figure that to be the fixed component. So the example, we'll use the mixed cost equation. And how does that work? Well, the mixed cost, we've got y equals Vx plus f. We're going to insert either high or low data point and solve for f. Okay, so using the previous example, y, well, from the data that we have is 209,600. You can go back in the slides to look. And that equals $8, which the 8 is what we figured out earlier, 25,200 plus the fix. So in our previous data, we know that our total costs were 209,600. We know that it's $8, our variable portion is $8. We solved for that in our first step. and $8 times the 25,000 units plus the fixed cost is going to be our total cost. So we'll solve for F. In this case, F is going to be equal to 8,000. So our fixed portion of this equation is 8,000. Or we could go on the other side. We could just use the low plot. We know that that was 114,000, and that also equals $8 times the low number of units was 13,250 plus the fixed cost. But we should still get the same. If this all works, F is still going to be equal to 8,000. We initially in the first step we figured out what the variable cost per unit was. Now we've solved for what the fixed portion is. So this is the HighLow method, step 3. And then from here, then using the amounts solved for in the amounts solved for in steps 1 and 2, write the equation representing the costs behavior. So the example for this equation would be y, the total costs are going to be equal to, well, we know what the variable cost per units times, not times, but 8x, x is the number of units, that's the unknown variable now, plus 8,000. So in the first two steps, the first steps we figured out that our variable cost is $8 per unit. And then in the second step we figured out that our fixed cost is 8,000. So from here, I'm sorry, you probably couldn't even see most of that, but using the amount solved for in steps 1 and 2, we write the equation representing the cost behavior. The example is y equals 8x plus 8,000. 8 represented the variable cost per unit that we figured out in step number 1, and then plus the 8,000. 8,000 is our fixed portion that we figured out in step number 2. So now this equation, all we have to know is what is our volumes. Once we know what our volumes are, that's the X. Once we know what the number of units we're going to be producing, we'll get that from our salespeople. They'll tell us what our production is. Well, they'll tell us what the sales are, and then we'll figure out what production we need. Once we know what production we need, then we can use that to solve for what our total costs are going to be. So HighLow method conclusions. The advantages, well, one, it's simple. I can type it. What else? It follows a familiar y equals mx plus b. There are some disadvantages with it, like with everything. Disadvantages, and the disadvantage would be only uses 2 data points. In other words, I'm not so sure how accurate it will be when we're only using 2 data points. We might conclude that, oh no, that's not as accurate as we need it to be. So that would be a disadvantage. Okay, so the next way we can analyze information is what's called, let me go ahead and, regression analysis. And when we talk about regression analysis, we're talking about a statistical procedure for determining the line and cost equation that best fit all of the data points in the data set. And so the line of best fit. Okay, so This is probably more accurate than the HighLow method. R-square, this is the statistic, tells us how well the line fits the data points, which is also referred to as the goodness of fit. And then finally, this is usually completed in Microsoft Excel. Okay, so moving on, we have R-square. And this is the higher the R-square, the stronger the relationship between cost and volumes. So the R-squared, or range, from 0 to 1. So think of it in terms of a percentage. 0 would be no, it's very, very weak. There's weakness, there's no relationship at all. 1 would be 100%. So there'd be the strongest correlation. And then the rule of thumb, what is the rule of thumb? So, R square, if it's greater than 0.8, that would indicate, 8.8 indicates very reliable cost equation. R square between 0.5 and 0.8 should be used with caution. And R square, which is less than 0.5, indicates equation is not reliable. So we're hoping that whenever we do the analysis using the analysis elements, we'll get something that gives us a pretty strong correlation. We're looking for a 0.8 or better. Something between 0.5 and 0.8 still might be useful, but we'll be careful with that. And anything less than 0.5 is a waste of time. We probably won't even look at that. Okay. Here's kind of a graphical representation. Okay, so R squares, in essence, we have a plot all over the place here. You can see that the data plots, if you actually run the numbers would actually plot a line based upon those data points, something like this. But, there may be 0 correlation, so this is the lowest possible value. That means it's difficult to really judge where things are going to be in the future when things are so scattered this way. By the same token, if you have everything lined up perfectly, then this is a very, very strong correlation. There's no question that all these data points lined up perfectly, so we could rely on this heavily, right? This is an example of R square equals 0. This would be an example of R square equal 1. In most cases, something's going to fall in between this R square of 0 and R square of 1, but you can see the extremes and know what we mean by that. Okay, so data concerns. Whenever we're using this method, we also have to be concerned about the data. Only valid within the relevant range. And remember, the relevant range is really referring to volumes. Within that volumes, we'll have, we'll make sure that we'll be okay. We also need to take into consideration that there may be some seasonality associated with our production. All right, that may make our data less reliable. We also need to remember that maybe we're in an inflationary, if we're in an inflationary situation, then the data becomes less relevant or less reliable. And then again, we got to watch out for those what is referred to as outliers, right? And that may mean that you may need to remove outliers from the data set. It helps make sure that we address the data concerns.